Okay, welcome to EGR 456. In today's class, we are going to talk about the linearization, and this is important because this information will be useful when you design and implement autopilot. Once again, what I'm going to do is I'm going to go back and review the information that we discussed in a few classes ago, and then I will talk about how to do this linearization and transfer function analysis using Matlab. And I will also talk about the rubric. So just to tell you that the rubric is already posted, and hopefully you will be able to take a look at the rubric. So what we are going to do in today's class, we are going to go back and review the lateral and longitudinal transfer function and dynamics. So first and foremost, the deadline for project 5 has been extended. So please make yourself familiar with the due dates. And just a second here. Okay. Good. Now my Apple Pencil is working. So we started with the equations given on the Genesis block. And now what we want to do is we want to derive a linearized system for the lateral transfer function or the lateral dynamics and the linear dynamics. Now, let me start by outlining what we want to do. So first and foremost, let's start with the lateral dynamics equations. Now, the chapter, the section that you should be focusing on for this particular project is section 5.5. So please review this section 5.5 before you work out the project. And once again, the project has some components. It can be done multiple ways. So whatever way you are comfortable, we can actually use those techniques. So first and foremost, what are we trying to do here? We are trying to linearize lateral dynamics. Now, first, what do we mean by lateral dynamics? So if you have an aircraft, so aircraft has a longitudinal plane. So this is the longitudinal plane. And the aircraft has a lateral plane. So we are at this point interested in the lateral dynamics. So lateral dynamics. Now, what are the variables that affect the lateral dynamics? So the lateral dynamics clearly is, I'm gonna assign north east and down. So this is north, this is east, and this is down. So lateral dynamics takes place in the northeast plane. So we are focusing on northeast plane. And the variables that are important for lateral dynamics are V. So once again, let's understand this is X, this is Y, this is Z. The variables are V. Then you have P, which is P. You have R. I showed, so P is in this direction. P. You have R. Then you have phi, which is the roll, and you have psi, that is the yaw. So the variables or states in lateral dynamics are V, P, R, phi, and psi. So what this implies is the derivative of these states should be 0 for the trimming in lateral dynamics. So that is the first part. The second part is, let's look at the control. So if you look at the lateral dynamics, your control is going to be aileron, and you're going to have a rudder. So yes, so V is body velocity. In Y, P is angular radians per second about X. R is angular velocity radians per second about Z. Phi is radians about X, and psi is radians about Z. So this is roll, this is yaw. And this is important because these are the variables that we have to trim. So there are two ways to do this. And if you look at the textbook, I want you to look at the equations that are given on page 61. So if you look at page equations on page 61 and 62, which are the same 12 state equations. Out of those, what we need to do is we have to look at the equations that are corresponding to the derivatives of V dot, P dot, R dot, phi dot, and psi dot. So these equations, they need to be trimmed. So what this means is equation 5.5, 5.10, 5.12, 5.7, and 5.9. They need to be trimmed. And once these equations are trimmed, what you want to do is you want to use the results for this trimming to be fed into your state space, into your model, and generate transfer function or state space matrices. So A, B, C, D. Now, let me explain this once again, what we are trying to do before I jump to Matlab. So we have 12 equations. And out of that, for lateral dynamics, 6 equations should be trimmed. So nobody stopped you from trimming additional equations, but at least the 6 equations, they should be trimmed. So what you are going to do is you have this nonlinear equations. Then you are going to trim them or find steady state. Use this steady state to linearize. Use steady state to linearize. And this can be done inside Matlab. Alternatively, what you can do is you can manually do the trimming. So I will just make a note here how to do it manually. So to answer this question, I want you to look at page 80 on the textbook, wherein they have given you the state space form of these equations already. So if you look at the equations, and this matrix is 5 by 5. And then here, again, you have a matrix, and then you have delta A and delta R. So V, P, R, V, psi. So you have all these equations. So basically, these entries, and this equation is 5.43 from the textbook. And the terms here are defined in table 5.1. This equation is 5.43. So what you can do is you can directly go to this equation, then use the values, the numerical values for Zagi, and then you can find out this matrix. This is your A matrix, and this is your B matrix in number. So you can find the numerical value for matrix A and matrix B, and then you can use SS to TF to find out the transfer function using Matlab. So I would explain this once again. So you have two options. Option 1, find values for Sagi using table 5.1. Substitute these values in 5.43, and 5.43 is something like a x plus b u, and you can use state space to transfer function a b c d to find out the transfer function. This is one option. Option 2 is start with 12 equations which are nonlinear and trim the equations, and there is some trial and error that is needed. Trim the equations so that v dot is equal to 0, p dot is equal to 0, r dot is equal to 0, c dot is equal to 0, and psi dot is equal to 0. This is required trim in lateral direction. And what this means is your aircraft which is flying, that could be very well accelerating in the longitudinal direction or changing in altitude, but in the lateral direction, in this lateral plane, the aircraft is at an operating point. So what this means is the aircraft is in steady state in lateral direction or northeast plane. Okay, so these are two options for you. You can actually, if you want to, if you don't like the equations the way they are given here, you are welcome to use equation given as 5.44, and that would give you similar answer. So you can use either 5.43 or equation 5.44. That is just a different representation of the dynamics equations. Now I want to take a minute and talk about the project or the problem that we are trying to solve, and so that it's very clear what is required. So in problem 5.6, what you want to do is Matlab script using and use trim. Then in 5.7, use linmod. In 5.8, we have to do a long, which means find, linearize system of equations in longitudinal direction, you can also look at the transfer function and then find eigenvalues of A, alternatively, or poles of transfer function, because eigenvalues in time domain are the poles in the frequency domain. Now, next thing is, he's saying that when you have an aircraft which is trimmed in the longitudinal direction, so when the aircraft is trimmed in the longitudinal direction, this aircraft exhibits phugoid. It exhibits short period and it exhibits different trimming conditions. So if you look at the problem, you have the phugoid, then you can actually look at the behavior of the system. So what you would see is, you will see modes related to phugoid, and then you will see the, so essentially you have to apply the step input. Now, the way this is written here, because the authors intended these exercises to be independent of any toolbox, and the textbook was written in 2012, and the new toolboxes were not available. But with aerospace toolbox and the steady state analyzer and the control linearizer, so if you have access to Linearizer toolbox, all this can be done in one shot. And I will explain it to you, and I'll show it to you how it is done. Next, look at problem 5.9. And I would like to work out the problem 5.9 first. So in 5.9, we have to find out a lat, which means the linearization in the lateral direction. And then it is saying that notice there is a zero eigenvalue. In other words, you have a pole at 0. Then notice you have an eigenvalue which is real. Then notice you have a complex conjugate pair. And these eigenvalues are associated with Dutch roll motion. So this is associated with spiral divergence. It's a roll motion, and then spiral divergence. So what we are going to do is, and all of this can be done with the Linearize toolbox. So in the lateral mode, and actually this project, once you understand what is expected, this project is very simple and can be done in 5 minutes. And I'll walk you through this. So now what this is saying, that consider the motion of the aircraft in the lateral plane and show that the eigenvalues of the linearized system exhibit these characteristics. And eigenvalues of the linearized system, they exhibit certain motion of the aircraft. And I would strongly recommend at this point to see yourself visualization of a Dutch roll, spiral divergence, phugoid, and short period mode. So it is very important that you are able to correlate with the values that you get with the actual behavior of the aircraft. Now I'm going to go to Matlab, but before I go to Matlab, everyone understood what we are trying to do here? We are trying to find out an approximate dynamical system. So lambda is equal to 0. So lambda is equal to 0, which is not a steady state. It just it's sort of a free motion mode. So what it means is, if you have a system, and I'll try to explain this with if you have a system like this, which is free to go on either side, you will see that one of the lambdas is going to be 0. So one of the lambdas is 0. That actually means it's a sort of a free motion. If your eigenvalues are purely imaginary, then the system is marginally stable. Now, there is something else that I won't discuss in detail, but if you have a 0 eigenvalue, you want to be a little bit of careful. When you have an eigenvalue that is 0, you have to look at additional test to decide on the stability. So that is what it is, and I will explain it to you as we work through the problem. But most important, that as I explain you the problem, I'm gonna till I set up my Matlab, please go to YouTube or just visualize or view what do we mean by phugoid mode, what do we mean by short period mode, what do we mean by Dutch roll mode, what do we mean by roll mode, and so on. And if you really want the discussion of what these modes are, I would recommend you to look at section 5.6 from the text. And they actually talk about what is the phugoid mode. But unfortunately, they don't give any pictures. So I would encourage you to look at the actual pictures and videos for these different modes. So to be honest with you, you don't really need to use LinMod. And the reason for that is, when this textbook was written, these additional toolboxes were not available. But since I have taught you how to do the linearization, I taught you. So here is what I taught you. I taught you how to use LinMod. And I also used how to use the Simulink Linearizer. And there are certain advantages in using Simulink Linearizer, because you have better control over the algorithms, the options, and you can gain more insight using Simulink Linearizer than LinMod. So I just want to, before I proceed, I just want to briefly talk about Rubric. So someone just asked me, I think, yeah, Travis just asked me a question about the Rubric. So I just want to talk about the Rubric for project 5. So 5.6 and 5.7, you are welcome to do it, but it's just for verification. So 5.6 and 5.7 is creating the Matlab script, because what you can do is, once you do it in Simulink or when you use a Simulink linearizer, you can use Simulink linearizer to create a Matlab script. Five 5.7 is asking for linmod. You are welcome to try it and compare the results, but this is something optional. However, most of your grade is dependent on 5.8 and 5.9. In 5.8, if you look at the rubric, you will have to first use the linear system toolbox, or you have to linearize system. Linearize the system. And then find eigenvalues and explain. Again, in 5.9, linearize the system. First, this is for longitudinal, and this is for lateral. Find eigenvalues and then explain. So the snapshots, so you can include the snapshots of the eigenvalues. This is 2 points. And linearizing system and explaining is 3 points. So you need to explain what it means, and you are welcome to refer your model to the linearized model that the author derived. But I will explain to you what is the difference when we do the linearization using Matlab and when we do the linearization the way discussed by the author. So what you would turn in? You will turn in snapshots. And here you will turn in your Matlab, Simulink file. You are welcome to include snapshots here so that the grader, and then you have to explain what those results mean. Okay, before I jump in working out the problem, everyone clear? This project I think is due Saturday. (11:59 p.m.) Okay, any questions? Does that answer your question, Michael? Okay, any other questions before I start my Matlab? Yes, we will use, yes, Jessica, to answer your question, we'll use the same file from project 4. Okay. And it may look like that I'm giving you about 90% of the solution. But as long as you understand the material, that's all good. So I'm going to start my Matlab, but I trust that you have quickly watched the videos for phugoid mode, short period mode, Dutch roll, and divergence. So I'm going to trust that. All right, I'm going to start my Matlab. And one thing I want to tell you, that whenever we have something like trimming, you may be able to trim the aircraft in the first iteration, or you may not. So there is always trial and error. But what we need to do is we need to kind of understand what we are looking for. So first, we are going to look at the lateral dynamics. So I'm working out problem 5.9. Okay, I'm working out problem 5.9. If you want, just read through the project real quick for a minute, and that will set us up. Okay. So can you see my screen? I need to set up my chat window so that, okay. All right. So this is my screen. And what I'm showing you is the same script that we worked on in last class. Same script as project 4. Same script as project 4. And please follow my lead. It's always a good idea before you start to see if your baseline simulation is working. So we would run the simulation and hope there are no errors, and see if the simulation is running. Yeah, so I didn't see any errors. Now what I want to do is, I'm gonna stop the simulation for a second. Go back to the Simulink. I'm gonna go back to the Simulink and go to Linearization. Go back to Simulink and go to Linearization. If you remember, in last class, we used Steady State Manager for trimming. In today's class, we will use Model Linearizer. Everybody sees Model Linearizer? If you are not able to see it, here is what you do. You go to Apps, drop down, and then you should be able to see Model Linearizer here. This is the same app that I used 2 lessons ago for demonstration. Click on Model Linearizer. And as soon as you click on Model Linearizer, this Model Linearizer opens. Now what I want to do is, I want to actually, I'm gonna delete the trims. So clear. So now this is what you should have. Then what I'm gonna do is model IOs, keep them as model IOs. Here, I'm going to trim the model. So I will trim the model. Okay. Now, if you get this error, get input struct operating trim, and what it means is most likely, if you go to preferences, add-ons, app designer. Okay. So what this means is, let me see for a second. Linearization. What this means is I need to clear the previous session, which I actually tried to linearize. So bear with me just a second. Yeah, we will try to trim it. We will try to trim it. But then what's happening is it's giving me an error and saying that op trim 1 is not known, and that happens because, and I'm trying to see where that op trim is here. Yeah, it's not here. So I need to actually, you should not get this error because you don't have any op trim, non-minimal state, state ordering, zero order hold. It's not here. Let me go back. So no, go back to simulation, then go back to modeling, model settings, model settings. Yeah, it's a model setting. That's correct. I need to take, thank you, Travis. Here, just, so check this out, op trim 1, click OK, and you should be good. Thank you, Travis. Now what I'm gonna do is, I'm gonna go to apps, I'm gonna go to model linearizer, and now see if it is working. And it should work now. Okay, go to trim model, and can you see that that error disappeared? Okay, now what I need to do is, I need to trim the model in lateral direction. And it's not straightforward because the states here are given at state 1, state 2, state 3, all the way to state 12. Just for my reference, I'm going to open up the states. And I'm going to try, this is just for my reference. So I'm going to open up the states trim model. Where did my trim model go? Don't see it here. Let me open this again. Click on, it likes to hide. Oh yeah. Yeah. That is Matlab for you. Model Linearizer. Trim model. Okay, finally. So now here is what I'm gonna do. Okay, now what I want to do is, I just bear with me for a second. Pn is state 1, Pe is state 2, Pd is state 3, U, V, W. So now I want you quickly to look at the nodes. We want V dot to be 0. If I want V dot to be 0, and V dot is state 5, so which means the state 5 should be 0. Are you with me so far? The next thing is P dot should be 0, so which is state 10. So derivative corresponding to state 10 has to be 0. Next is R, which is state 12. So the derivative corresponding to state 12 has to be 0. Then next is phi dot. Phi is state 7. Phi is state 7. So phi dot has to be 0. And then psi is state 9. So state 9 has to be 0. And I'm going to pause here for a minute so that everyone can click on steady state for state 5, state 7, state 9, state 10, and state 12. Are you with me so far? We are doing this for lateral dynamics. So all the lateral dynamics. Now, at this point, it may be tempting, and just pause here for a minute. At this point, it may be tempting to trim the model. Okay. Please note, we haven't changed anything in the input. We haven't changed anything in the output. And for Zagi, what you want to do is since your rudder is 0, so you would have to set this value equal to 0 because Zagi does not have rudder. So Zagi does not have rudder. So I would just set this up to 0. Now what I'm going to do is, just don't try this yet. Just wait for me to finish this. It may be tempting to just click start trimming. It may be tempting. Let's see what happens. And then you will see that with these minimal constraints, trimming solution OP trim has been found out. Now I want you to click and see if you are able to get OP trim. OP trim 1 you may not get if your settings are different than my settings, but I'll wait for a minute to see if anyone is having any issues with OP trim 1. So please run OP trim. Just try to trim. Thank you, Jessica. Anyone else? Okay. Now what I want you to do is, I want you to highlight this OP trim. And at this point, my main aim is to see that the desired states, which I started with, and those states are state 5. Can you see state 5 derivative is 0? State 7, this state 7 derivative is 0. So state 7, cannot highlight, state 7 derivative is 0. State 9 derivative is 0. State 10 derivative is 0. State 12 derivative is 0. Can you confirm that your state derivatives are zeros for the trim case? Next thing is, I want you to confirm if your inputs have some meaningful value. In other words, you don't have inputs that are like minus infinity or minus 5,000, minus 10,000, no weird inputs. So this seems reasonable to me. It seems to me that there is some aileron value, and clearly we need to have something here that I need to clarify. Absolutely. Everyone, please click on this input block. Can you notice that your first input is 0? Your second input is a non-zero value. Your third input, look at the actual value, Zubir. Actual value is a non-zero value. Now what this means, and I want you to absolutely understand this. Input 1 corresponds to elevator. We do not use elevator in lateral dynamics. Once again, we do not use elevator in lateral dynamics. We are only going to control lateral dynamics by means of ailerons. And that's why you have input in ailerons. We are using Zagi. Zagi does not have rudder. So clearly this is 0. But we have a non-zero value of thrust. That's why you have input 4, which is LN4. Everyone clear? No input 1. Here there is no input. Here there is no input because we are in lateral dynamics. Lateral dynamics for Zagi is only controlled using ailerons and thrust. Now what I want you to do is take a moment and look at the output. Now the output is, the first is the airspeed, VA. Second one is angle of attack. And third one is side slip. So now you will see here is you have some non-zero output 1. That is okay. You have some non-zero output for angle of attack. That's okay too. And you have some non-zero output for side slip. That's okay too. At this point, if you want to add additional constraints, you can. At this point, if you want to add additional constraints, you can. Now, what I'm going to say here is, and please follow this very carefully, I'm going to say my airspeed is 10 meters per second. So I could add 10 meters per second airspeed. This is not required, but you can add it and then just start trimming and see if it works. Why am I saying my state 4 is 10? Because that's what we did in the earlier trimming. We said the airspeed is 10, the flight path angle is 0, and so on. So I'm just going to say start trimming and see if I get a solution. And I may get a solution, I may not. That's totally okay. But the good news is I got a solution. We are looking at the lateral dynamics. That's why we are not focusing on the elevation. Elevation affects in the longitudinal. Okay, we can actually, if you want, we can add elevation too. Just a second, boy. So now again, I want you to check, and the most important thing is your trim variables are satisfied. What I mean by that, and now I know you know, state 5 derivative is 0, state 7 derivative is 0, state 9 derivative is 0, state 10 derivative is 0, state 12 derivative is 0. Then look at the inputs. You will see the input values have changed. And clearly now the thrust vector is more because we want some airspeed. Look at the output. And now you would observe that my airspeed is 9.8, which is close to 10 that we talked about. Are you comfortable with this? Everyone understands? Just to answer Borna's question, I want you to think about the aircraft as if you are looking in the top view. So your dynamics is in the top view. That's why we are not adding anything else. Now what I'm going to do is, yeah, thrust values are fine. My thrust value is quite small too. That's totally okay. Now, at this point, if you want to answer the first question of the project, you can use this to generate a Matlab script. Click on the Matlab script and boom, your Matlab script is generated for you. Can you see that your Matlab script is generated for you? And I just want to point out few things here. Op spec states are the values, initial values that you want to be maintained as constant. So as you can see, our airspeed was 10. Now, if you look at the steady state, this op spec steady state, you will notice state 5 is in steady state. State 7 is true, that indicates it's in steady state. State 9 is in steady state, 10 and 12. So these are basically, this is the script that is actually can be used to create the lin. So instead of linmod, it's using find op, which is same as linmod actually. So you specify a model, specs, and the parameters. So find op is same as linmod. Okay, I'm gonna pause here for a second before I go to the next part. Everyone okay so far? Any questions? Anyone did not get answer or has questions? Should we expect the derivatives of states 5, 7? That's what is happening. So if you go to states, look at the dx. Dx are the derivatives. I'm not worried about actual values. But if you want I can spend a minute on the actual values. So what these actual values are telling me, and you need to see those in conjunction with your states. So your state psi, so 9, 10, 11. Look at 9, 10, and 11. So roll pitch and yaw are close to 0, which means your aircraft. And if you don't believe me, you can just run the simulation and verify that yourself. You can actually, you can go back. You can initialize model. Click here, initialize model. Initialize model, and then run the simulation, and you will see that aircraft will be in longitudinal trim state. Alejandro, it is the same script that we used in last class, to be honest with you. So you might want to go back. Yeah, it's the same file. Okay. Now, if you want, you can initialize the model, go to your Simulink, and go to the simulation and hit run, and you will see the aircraft is trimmed in the lateral direction. However, what I want to do is, I want to go back. I want to go back and go back to the linearizer. So I am looking for my linearizer. Just a second here. Model linearizer. And what I'm going to do now, and this next part is important. So everyone, please pay attention. Just make sure you have op trim 1 and op trim 2, both of these visible in the linear analysis workspace. Click on result viewer, click on linear advisor. So I'm going to stop here. So what would happen, Zubir, is Matlab is so smart that it will give you, it will highlight in red if any of these specifications are not met, then there will be it will be highlighted in red. If there is no red highlight, then most likely everything is good. Okay, now what I want you to do is go to result viewer and go to linearization advisor. And now what I'm going to do is I'm going to do something interesting. And now I want you, this is not, we did not use this in last class, but I want you to open this whole palette. And first and foremost, I'm going to click on pole 0 map. Can you see this pole 0 map? And I'm going to observe what happens as soon as I click on, and I'm going to select operating trim 2. So please select OP trim 2. Once again, select OP trim 2, go down here, click on pole 0 map, and see what happens. It will linearize the model in the lateral direction. Oh, come on. Now this gives me an error because accelerator mode is not utilized. So I need to go back to simulation, go with the normal mode. So change this to normal mode, select OP trim, go back and do pole 0 again. And then here is what has happened. I now have a linearized system. I have this linearized system. Now, if you want this system to be expressed in state transfer function, click on the transfer function and boom, this is the transfer function that you got. Now, a step here, you will recognize what this is. Transfer function is always between a single input and single output. Single input and single output. you notice the denominator of this guy, denominator of this guy, denominator of this guy, and denominator of this guy, they are one and the same. Now, I'm gonna go back to the plots, again, linear analysis, and I will try to plot poles and zeros. And when I click on so I can actually do a step response. I'm gonna view it for a second. Plots and results. So I want you to first get poles and zeros map. And I'm gonna wait here for a second before I jump into discussion. So I want you to get this pole zero map. By mistake, I clicked this 2 times. That's why I have 2 plots, but you should actually get just 1 plot. Have you gotten this pole zero map? All right. Are you ready for the magic? They should be close, Joseph. They should be close. Are you ready for the magic? So please note, there are no zeros. These x's are poles. So click here. You will notice you have one pole which is complex conjugate, one pole which is complex conjugate, one pole which is complex conjugate with a negative real part. And at this moment, let me see if my project 5 is up. In project 5, here is what he's asking. First, so when we computed poles, we computed eigenvalues. So please note that there is an eigenvalue at 0. Can you see that there is an eigenvalue at 0? Everyone, can you see that there is an eigenvalue at 0? Can you see that there is a real eigenvalue in the right half plane? Can you see that there is a real eigenvalue in the right half plane? This dotted line is an imaginary axis. Can you see that? Yeah. We will get there. Just a second, Joseph, just a second. So can you see that there is a real eigenvalue in the right half plane? A real eigenvalue in the left half plane? Okay, just a second. Just a second, Travis. Real eigenvalue in the left half plane? And can you see that there is a complex conjugate pair? So what it means is we actually got all the eigenvalues that he's asking in 5.9. Any questions at this point? Oh, to get rid of accelerator mode, go to the simulation. Here, go to the below stop sign. You have normal, accelerator, rapid accelerator. Click on normal mode. Okay, no. So there is some more to it. So hold your horses. Now what I'm going to do is I'm going to try to look at the step plot. So what this shows me the step response of the system. Now, the step response of the system is indicative of the behavior of the system in the eigen, when the eigenvalues are in the left hand plane or right half plane and so on. So you can actually study the step plot and see that the modes which are like spiral divergence mode, which is actually indicative of instability and other stuff, is visible. So what you can do is you can actually create a step plot. And you will notice that step plot, and that will be visible, the step plot here. You will notice this instabilities that we are talking about. Now, next thing what I want to talk about is I just want to talk about this impulse and see what happens. You will also notice that I see the divergence that is expressed, and that this impulse is diverging because if you look at pole zero map. Okay, Joseph, just a second for a minute. Sorry, just a second. Wait for a second. Let me explain. So all this is because of these unstable poles. So if you really want to get rid of these unstable poles, okay, how would you get rid of these unstable poles? To get rid of these unstable poles, you will have to multiply, and I want to go back to the project 5. You have to place a unit doublet on aileron, and only then so you need to get rid of these poles. If you don't get rid of these poles, you are gonna have instability. So you will have instability if these poles are not. So just a second here, delete. So you will have to get rid of these poles to make sure the system oscillates. But if you have these poles, then you will notice that a system is gonna be unstable. Now the next question is, how do you get rid of these poles? And to get rid of these poles, what you need to do is you need to design a control system. What you need to do is you need to design a control system that would push these poles. And I'm gonna see if that option is here. Let me see if that option is here. So what you wanna do, this is the pole zero map. And so this is actually telling me which of these states are actually unstable. So this gives me the complete pole zero map. No, you will have unstable poles because that unstable pole exists in lateral dynamics. And that's what this file, if you look at 5.9, it's asking you to convince yourself. Just a second here. It's asking you, let me see pole zero map. Where is my first pole zero? Okay, let me just create a pole zero map. So this lateral is asking us to convince ourselves that the eigenvalues shown over here exist in the pole zero map. Or looking for my map. Okay, it's visible in this map. If I were to do IO pole map, that actually I'll explain this to you in just a second. Oh, okay. Probably here is why you didn't get one. Did you use optrim 2 or did you use optrim 1? Okay. Okay, so that is what you should be getting. And that makes the system unstable. And you can very well verify this by taking this A matrix and finding out its eigenvalues. You can take this matrix and find out its eigenvalues, and that will tell you the exact same thing. Okay, any questions here? Now, I've solved 5.9 completely for you, which means you should be able to get 5 points. Yeah, actually I made a mistake. So you can click on linksys. I would just, it's just the advisor. So I wouldn't. So linksys 1. Yeah. So you can delete this, clear, 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 clear. The only thing what you should have is OP trim 2. And then for OP trim 2, you should linearize. And then it will give you this map. And it will, so forget about it. It will give you this map. And this will give you the transfer function and state space. So if you take this A matrix and find the eigenvalues, you will notice that your eigenvalues will be exactly the way it is in the lateral dynamics. Now, at this point, before I close the discussion, some of you may ask me, is wow, that is great. But then why does the system of equations given in 5.43 only has 5 state, not 6? And the reason for that is there is a substitution that is being done, and that substitution basically reduces one set of equations. So what, if you were to look at it, what you will observe that this substitution reduces one equation. Yes. And at this point, I want to ask you this question. Can you do 5.8? Can you do 5.8 and perform the exact same analysis for a longitudinal transfer function? Yes, but you need to explain as well. You need to show all these plots and make sure that my analysis is correct. Ideally, the only thing that I could think of is if your trim values are not same as my trim values. So I I would encourage you to just look at your trimming, see if your trim values are same as my trim values. And they could not be the same is because if your algorithm, so I'm going to go back a step, and what I'm going to do is maybe your trimming algorithm is not the same. So I would check if the trimming algorithm is different, then your answers could be different. And again, it's a numerical technique, so it's a nonlinear equation, so it may be that your answers would be different. But you should be able to get, in general, same result. I'm going to stop recording here.